It is recommended to tie both the remote 200 amp panel board and the main distribution panel, often referred to as the MDP, into the concrete encased grounding grid. There are several reasons why this approach is beneficial. Firstly, NFPA 70, which is the National Electrical Code, has specific requirements for grounding. Section 250.32 A5 of the NEC requires that all electrical equipment and metal raceways be grounded to a grounding electrode system. Section 250.56 A requires that a grounding electrode system include one or more grounding electrodes, such as a concrete encased grounding grid. Secondly, a concrete encased grounding grid provides improved grounding. This type of grid provides a low resistance path for electrical current to flow to earth, ensuring a better ground connection for both the MDP and the remote panel board. This configuration reduces the risk of electrical shock, equipment damage, and fire. Thirdly, surge protection is enhanced. The concrete encased grounding grid acts as a surge suppressor, diverting excess electrical energy to the ground. This helps protect sensitive electronic equipment such as computers from damage caused by power surges. Fourthly, maintenance is simplified. By connecting both the MDP and the remote panel board to the same grounding grid, a centralized grounding point is created for the entire electrical system. This simplifies maintenance and troubleshooting, as you only need to maintain a single grounding electrode system. To tie the remote panel board into the concrete encased grounding grid, a grounding conductor sized according to the NEC table 250.66 should be used. The grounding conductor should be connected to the grounding busbar in the remote panel board and to the grounding electrode conductor at the grounding grid. The purpose of a grounding system is to provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices such as circuit breakers and fuses. A well-designed grounding system also minimizes voltage differences between conductive parts, reducing the risk of electrical shock. Concrete encased electrodes, often referred to as UFO grounds, are particularly effective due to the large surface area in contact with the earth and the moisture-retentive properties of concrete. This results in a low grounding resistance compared to driven ground rods alone. When installing a concrete encased electrode, it is important to ensure that it meets the requirements of the NEC. This includes using at least 20 feet of bare copper conductor that is at least 4 American wire gauge in size. The conductor must be encased in at least 2 inches of concrete and located within the bottom of a concrete foundation or footing that is in direct contact with the earth. For optimal performance, the concrete encased electrode should be supplemented with other grounding electrodes, such as ground rods or ground rings. The connection between the grounding electrode conductor and the concrete encased electrode must be accessible and made with a listed connector suitable for direct burial. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. This includes measuring the grounding resistance using a ground resistance tester and visually inspecting the connections for corrosion or damage. Any deficiencies should be promptly addressed to maintain the integrity of the grounding system. In addition to the concrete encased electrode, ground rods are commonly used as grounding electrodes. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to provide a path for fault current. The NEC requires that ground rods be at least 8 feet in length and have a minimum diameter of 5/8 inch, unless listed for use with a smaller size. When installing ground rods, it is important to drive them deep enough to reach permanently moist soil. This helps to reduce the grounding resistance and improve the effectiveness of the grounding system. If multiple ground rods are used, they should be spaced at least 6 feet apart to avoid overlapping their areas of influence. The connection between the grounding electrode conductor and the ground rod must be made with a listed connector suitable for direct burial. Another type of grounding electrode is a ground ring, which consists of a bare copper conductor that is buried in a continuous loop around the perimeter of a building. The ground ring must be buried at least 30 inches below the surface of the earth and must be at least 20 feet in length. Ground rings are particularly effective in areas with poor soil conductivity, as they provide a larger surface area for contact with the earth. The connection between the grounding electrode conductor and the ground ring must be made with a listed connector suitable for direct burial. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The grounding electrode conductor must be sized large enough to safely carry the maximum fault current that could occur in the system. It is important to use a grounding electrode conductor that is made of copper or other corrosion-resistant material to ensure a long-lasting and reliable connection. The grounding electrode conductor must be securely connected to the grounding electrode using a listed connector that is suitable for the type of electrode being used. In addition to grounding electrodes, bonding is an essential part of a comprehensive grounding system. Bonding involves connecting all non-current carrying metal parts of the electrical system together to create an electrically continuous path to ground. This includes metal raceways, enclosures, and equipment frames. Bonding helps to minimize voltage differences between conductive parts and provides a low impedance path for fault current to return to the source. The size of the bonding conductors is determined by the size of the circuit conductors, as specified in NEC Table 250.102. C1. The bonding conductors must be sized large enough to safely carry the maximum fault current that could occur in the circuit. It is important to use bonding conductors that are made of copper or other corrosion-resistant material to ensure a long-lasting and reliable connection. The bonding conductors must be securely connected to the metal parts using listed connectors that are suitable for the application. Surge protective devices, or SPDs, are an important component of a comprehensive surge protection system. SPD are designed to protect sensitive electronic equipment from voltage surges caused by lightning strikes, power line disturbances, and other transient events. SPD work by diverting excess voltage to ground, preventing it from reaching the protected equipment. SPD are typically installed at the service entrance, at distribution panels, and at individual equipment locations. The selection of an SPD depends on the voltage and current rating of the electrical system, as well as the type of equipment being protected. It is important to choose an SPD that is listed and labeled by a recognized testing laboratory, such as UL, to ensure that it meets safety and performance standards. When installing an SPD, it is important to follow the manufacturer's instructions and the requirements of the NEC. The SPD must be properly grounded to ensure that it can effectively divert surge current to ground. The grounding conductor for the SPD must be sized according to the manufacturer's instructions and must be connected to the grounding electrode system. Regular inspection and testing of SPD are essential to ensure their continued effectiveness. This includes visually inspecting the SPD for damage and testing its performance using a surge tester. Any SPD that are damaged or have failed should be promptly replaced. In addition to SPD, other surge protection measures can be implemented to further reduce the risk of damage from voltage surges. These include using surge suppressors on individual equipment, installing transient voltage surge suppressors on branch circuits, and implementing proper grounding and bonding practices throughout the electrical system. A well-designed and properly installed grounding system is essential for the safe and reliable operation of electrical equipment. By following the requirements of the NEC and implementing best practices for grounding and bonding, the risk of electrical shock, equipment damage, and fire can be significantly reduced. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. The NEC provides detailed requirements for grounding and bonding in Chapter 250. This chapter covers topics such as grounding electrode systems, grounding electrode conductors, bonding, equipment grounding, and surge protection. It is important to consult the NEC and other relevant standards when designing and installing a grounding system to ensure that it meets all applicable requirements. Proper grounding and bonding are essential for the safety of people and property. A well-designed and properly installed grounding system can help to prevent electrical shock, equipment damage, and fire. By following the requirements of the NEC and implementing best practices for grounding and bonding, electrical systems can be made safer and more reliable. Continuous maintenance and regular inspections can ensure the grounding system continues to function optimally, providing a safe environment. Grounding is a critical aspect of electrical safety and should not be overlooked.